So far, we have discussed specific types of control loops, what components are used in them, and some of the applications they are applied to, like flow, pressure, temperature, and level. In practice, however, many independent and interconnected loops are combined to control the working of a typical industrial plant. The following videos will introduce you to some of the methods of control currently being used in process industries. We'll begin with cascade control. Cascade control is a control system in which a secondary control loop, also referred to as slave, is set up to control a variable that is a major source of load disturbance for another primary control loop, also referred to as master. The controller of the primary loop determines the set point of the summing controller in the secondary loop. The control of a closed loop in a cascade mode exchanges three signals with the loop, two inputs and one output, and these are the measurement, referred to with the letter M, the set point, referred to with the letter C, and the signal to the valve, referred to with the letters SV. A cascade consists, if you recall, of two control loops, the primary loop or the master and the secondary loop or the slave. Each loop is fed with a set point and a measurement of the process variable. Each loop will then compare these two values, then trigger an action or an output signal. In a cascade mode, the output signal from the primary controller will not go to a valve, but serves as a set point for the secondary controller. So, to put it simply, cascade operation is then characterized by C2 equals SV1. To better illustrate these concepts, let's see some concrete examples. In this first example, you can see a typical furnace heating control setup used extensively in refineries and petrochemical plants. The temperature controller, pressure controller cascade includes two control loops, the secondary loop of pressure controller or slave controller and the primary loop of temperature controller or master controller. The flow of gas to the burners is linked with the gas pressure immediately upstream of the burner. If this pressure is constant, the gas flow will be relatively constant. If the gas network pressure varies, so will the pressure at the burner. The pressure controller then corrects the opening of the gas valve to stabilize the pressure at the set point value. Consequently, the furnace outlet temperature is not significantly modified. The secondary loop is also called the fast loop because it quickly dampens the effects of local pressure disturbances. Nevertheless, many disturbances that the pressure controller cannot counter are able to vary the furnace heating capacity and consequently the outlet temperature. These disturbances may be countered by a more sophisticated control system. The primary loop has the same function as if the valve signal of the temperature controller directly drove the valve. In the case of the cascade, this action goes through the pressure controller. When the furnace outlet temperature drops, the temperature controller increases the set point of the pressure controller, and the pressure controller then observes a pressure measurement lower than the set point and makes up for the difference between the measurement and the set point by increasing the opening of the gas valve. This second example shows a typical tank level control upstream a distilling column, also used extensively in refineries and petrochemical plants. The level controller flow controller cascade also includes two loops, the flow loop or the secondary loop and the level loop or the primary loop. The distilling column downstream of the tank is a process element which often does not adapt easily to sudden feed variations. The flow loop provides a constant flow with very little fluctuations. The level loop prevents slow drifts that would tend to fill or empty the tank. If the tank has a large volume in relation to the liquid flow, a perfectly constant level is not absolutely mandatory. On the other hand, the level can dampen variations in liquid flow occurring upstream of the process, as depicted here. Now, there are several ways to operate a cascade depending on the operating modes of the two controllers. The following table gives a brief summary of all the possible configurations. When the primary controller is set on manual or on auto, and the secondary controller is set on manual, then the operator directly chooses the output signal of the secondary controller. In case the secondary controller is set on auto, then the operator chooses the set point of the secondary controller. When the primary controller is set on manual and the secondary on cascade, then the operator chooses the output signal of the primary controller. This is equivalent to the second case, where the primary is on auto or manual and the secondary on auto. And finally, when the primary is set on auto and the secondary on cascade, then the operator chooses the set point of the primary controller and the latter sets that of the secondary controller. Now back to our figure here. When changing from auto mode to cascade mode, two cases may arise. SV1 is equal to C2 and SV1 is different from C2. In the first case, the cascade is said to be aligned. The mode change can take place without any disturbance to the process. In the second case, if the secondary controller is changed from auto mode to cascade mode, then this will cause a sudden change in the value of the set point C2, and this may disturb the process seriously. The output signal SV1 must first be modified in order to obtain the equality SV1 equals C2. For digital control systems, automatic alignment is often provided. Now, to disconnect, break, or open a cascade, we simply change the secondary controller to auto mode. In a conventional control system, it is sometimes necessary to align SV1, the output signal of the primary controller, and C2, the set point to the secondary controller, by modifying the value of C2.